Hello everyone, my name is Oded Zatz. Today I'm going to talk about fair correlation clustering in general graphs. This is a joint work with Roy Schwartz. So let's start by introducing correlation clustering. In this problem, we're given a graph where each edge is labeled with either a plus label or a minus label. Semantically, the nodes represents objects, and the plus edge represents similarity between these objects, and the minus edge represents dissimilarity between these objects. The goal is to partition the nodes into groups or a clustering, such that this clustering is the most with the labels of the edges. So for a given solution, plus edge is in agreement in this solution if the two nodes are in the same cluster, like this edge. A minus edge is in agreement in the solution if the nodes are in different clusters, like this edge. On the other end, a plus edge is in disagreement in the solution if its two nodes are in different clusters, like this edge. And a minus edge is in disagreement in the solution if its nodes are in the same cluster, like this one. So the immediate question is, can we find for a given graph a perfect solution, like a solution where all the edges are in agreement? So generally the question is no, because if our graph contains a cycle where all the edges are plus except the one, so we never can find a perfect solution. Each solution will have at least one edge which is in disagreement. So it makes sense to talk about objective functions for correlation clustering. We'll talk about three popular objective functions. The first one is called max agreement, where the objective is to maximize the weight of the edges that are in agreement. The second one is called min disagreement, where the objective is to minimize the weight of the edges that are in disagreement in a solution. There's also the max correlation objective, when the task is to maximize the difference between the weight of the edges that are in agreement and the weight of the edges that are in disagreement in a solution. All of these problems are known to be NP-hard. The correlation clustering problem was introduced by Bansal, Bloom, and Charla about 20 years ago, and it gained quite popularity since then. So what do we know about correlation clustering? For min disagreement for general graphs, the best known approximation algorithm achieves an approximation factor of order of log n, where n is the number of the nodes in the graph. For complete graphs, an approximation algorithm with a constant approximation factor was given in the original work. Since then, it was improved to almost a factor of 2. For max agreement, an approximation algorithm which achieved a half approximation was given in the original work, and since then it was improved to approximately 0.76 using STP relaxations. There were also more works on special cases, like bipartite graphs, and the problem where the number of clusters is constrained to be constant, and so on. In this work, we talk about fair correlation clustering. The fair variant of correlation clustering, the input contains also a color function for the nodes. In this example, each node is either yellow or orange. The goal of the problem remains the same, but now we have another constraint. The number of nodes of each color in a cluster needs to be the same. So the solution used in the previous example is not valid anymore, because in this cluster we have 3 yellow nodes, but 0 orange nodes. So we need to change the solution. And you can see that this is indeed a valid solution because each cluster contains the same number of orange nodes and yellow nodes. So in general, each node is associated with a number between 1 and k, where k is the number of colors, and we denote vi as all the nodes of color I in the graph. Generally, the input also contains the ratios of the colors. In the example above, we had the ratio of 1 to 1 because we had the same number of yellow and orange nodes. But we could have had like 20 yellow nodes and 30 orange nodes, for example. So each cluster must contain 2 yellow nodes for every 3 orange nodes. So what is the motivation for fair correlation clustering? Well, in general, fairness in machine learning algorithms is quite popular. The need arises when the object represents humans, and we don't want that the solution will be biased towards sensitive feature. In particular, fairness in clustering algorithms was introduced a few years ago for the k-central and k-median objectives. Since then, there were more works on fairness in clustering, and in particular, there were 2 works on fair correlation clustering. These works focused on fair min disagreement for complete graphs. In our work, we focus on fair min disagreement and fair max agreement, and we do it for general graphs. The first two theorems talk about Fermi disagreement, and they are hardness results. The last two theorems talk about Fermat's agreement. The first theorem states that if we have an instance with two colors and a uniform ratio between the colors, then there is no polynomial time approximation algorithm with a finite approximation factor, unless p equals np. If we talk about instances with more than two colors, then a bicriteria algorithm does not exist. Where a bicriteria means that the algorithm can deviate from the fairness constraints. That means that if we try to make it easy on our algorithm and allow it to break the fairness constraints by some bounded value, it is still not possible to achieve such an algorithm. The third theorem states that if we have an instance with two colors and a uniform ratio between the colors, then we can achieve an approximation factor of approximately 0.6. If we talk about a general instance with k colors, where k is greater or equal to 2, then we can achieve a bicriteria algorithm with an approximation factor of approximately 0.59. Now that theorem 3 is a true approximation, which is not bicriteria, it will output an fair solution. And theorem 4 outputs a bicriteria solution, which means that it might violate the fairness constraints with a bounded value. In this talk, we'll talk about theorem 1 and theorem 4. Let's start with the first theorem and show that Fermi disagreement is hard even for instances with two colors and a uniform ratio between the colors. To do that, we will create a reduction from three-partition to the problem of Fermi disagreement. So let's first introduce the problem of three-partition. In this problem, we're given n integers, where n equals 3 times some other integer L, and a threshold capital A, such that each of the n numbers is between a quarter A and a half A. Moreover, the sum of all the n numbers equals exactly L times capital A. The question in this problem is whether one can partition all the n numbers to triplets such that the sum of each triplet is exactly capital A. This problem is known to be NP-complete even when all the numbers in the input are polynomially bound in n. Let's look at an example. So say we have 12 numbers and a threshold of 100. You can see that all the numbers in the input are between 25 and 50. And the question is whether we can partition these numbers to triplets such that the sum of each number is exactly 100. So the answer is yes. Here is the partition. So we want to create a reduction from three-partition to our problem, Fermi disagreement. So we're given n integers, a1 till an, and a capital A, which is the threshold. We build a graph, which is the input for Fermi disagreement. So for each of the n numbers, we create a yellow clique. Each edge in this clique is a plus edge. So we have n such yellow cliques. Moreover, we have L orange cliques, where each clique is in the size of capital A, and the edge in each such orange clique is also a plus edge. After that, we connect all of the orange cliques with minus edges. So all the orange nodes are connected by some edge, a plus or a minus. We can draw this input like that also. Each circle here represents a clique with a plus edges in this clique. Like, for example, this is a yellow clique with A1 nodes and a plus edge in this clique. And you can see that all the orange cliques are connected with a minus edge. So the claim is that a three-partition instance has a valid partition if and only if the instance created from Fermi disagreement has a perfect solution, a perfect clustering. That means a clustering with the zero disagreements. So given a valid partition to triplets, it is easy to build a perfect clustering for the Fermi disagreement. On the other end, given a perfect clustering for Fermi disagreement, we need to convince ourselves that it should look exactly like that. And after we do that, it's immediate to get how to get the partition to triplets. So following this claim, you can see that there is no approximation algorithm with a finite approximation factor for frame disagreement, because otherwise we could solve three partition, and that is not possible unless P equals NP. Given the hardness results for frame disagreement, it is reasonable to move on to fair max agreement and try to approximate this objective. Let's start with an observation. This observation tries to upper bound the weight of minus edges which can be satisfied in an optimal solution to fair max agreement. So to understand this observation, let's look at an example. So say we have an instance to fair max agreement, and we have a clustering for that instance. We can create a matching between yellow nodes and orange nodes, and that each pair of matched nodes is in the same cluster. Note that each minus edge between matched nodes is necessarily unsatisfied. That means it's in disagreement, right? So the observation says that if we can find like the best matching between yellow nodes and orange nodes, such that the total weight of minus edges between matched nodes is minimized, then we can get an upper bound on the weight of minus edges which we can satisfy in any solution to that input. And that bound is like the total weight of minus edges in the graph minus the total weight of minus edges which are matched in this like best matching. This observation leads us to a simple half approximation. The simple half approximation algorithm said that we can choose between two possible solutions. One solution which is just a single cluster which contains all the nodes in the graph, and the other solution is the solution which corresponds to this best matching between yellow nodes and orange nodes. We call this best matching as M-. So note that the solution on the right satisfies all the plus edges in the input, and the solution on the left satisfies all the minus edges in the input which one can satisfy according to the observation. And that leads us to a half approximation for the problem. The next question is how to improve upon this ratio. To do that, we would like to solve the problem when it's constrained to only two clusters. That's because it's just easier to solve the problem when it's constrained. A similar approach was used in some previous works on correlation clustering, and that's what we would like to do now. So the question is, how much do we lose if we restrict ourselves to only two clusters comparing to the optimal solution which can contain any number of clusters? So let's look at some solution C which can contain more than two clusters. Let's compare it to a two-cluster solution. So first, let's take each cluster in C and put it with uniform probability in either S or the complement of S. And the solution which we output is just the result of this process. So we output S and complement S, which is just two clusters. So note that all the plus edges which were satisfied in C are still satisfied in the two-cluster solution. Also note that the mean of the weight, the minus edges which are satisfied in the two-cluster solution is at least half. It is exactly half of the weight of the minus edges which were satisfied in C. So that leads us to the following lemma, which states that for every cluster in C, there is a two-cluster solution whose value is greater or equal than the weight of the plus edges which are satisfied in C, plus half of the weight of the minus edges which are satisfied in C. So that lemma leads us to an algorithm for the non-restricted problem. So first we need an alpha approximation algorithm for the problem which is constrained to only two clusters. Once we have such an algorithm, we can choose the best between two solutions. Solution which this alpha approximation algorithm returns, and the solution induced by the best matching M-, which we used for the half approximation. So note that the value of this solution which we return is the maximum between alpha times the weight of the plus edges satisfied in some optimal solution, plus half of the weight of the minus edges which are satisfied in this optimal solution. So the maximum between that and just the weight of the minus edges which are satisfied in that optimal solution. One can show that this expression is larger or equal than 2 times alpha divided by 2 plus alpha. So, 2 plus alpha multiplied by the value of the optimal solution. So that leads us to lemma number 2, which states that if you have an alpha approximation algorithm for the restricted problem, when it's restricted to 2 clusters, then we obtain an 2 alpha divided by 2 plus alpha approximation algorithm for the problem when it's not restricted. Also note that if alpha is greater than 2/3, then that expression is greater than half. So that's what we aim for. So before we talk about the alpha approximation algorithm for the constraint problem, let's see if the same approach still holds for instances with more than 2 colors. So lemma 1, which referred to the cost of the constrained solution comparing to the non-constrained solution, we still gain the same value comparing to the non-constrained solution. But we no longer can find the best matching between nodes of different colors, the same matching we used for the half approximation. So we can no longer find that in polynomial time. So what we can do is to just choose a random matching. We can output a clustering in which each cluster contains pi random nodes of each color I. We call the pi's are the ratios between the colors. So one can show that the mean value of such random clustering is almost the total weight of minus edges in the graph. There's a small loss of little o of 1, and that's if we assume that the sum of the pi's is little o of n, which is a really reasonable assumption. So we get a matching lemma to the lemma we saw in the previous slide, which states that if we have an alpha approximation algorithm for the constraint problem, we can get a 2 alpha divided by 2 plus alpha approximation algorithm, but now we got another loss of little o of 1. So now we can focus on on solving the restricted problem. To solve the constraint problem, we can utilize the sticky Brownian motion approach used in the recent work to solve the max cut with side constraints problem. In this problem, we are given a graph and the sets f1 to fk. It's actually a subset of b, and we're given a cardinality bounds b1 to bk. The goal is to find a subset S that maximizes the total weight of edges that cross the cut. That means that's a max cut problem. But the interesting constraint here is that there should be exactly bi nodes from each fi in this subset S. So we can use this problem, but first we need to generalize it to handle plus edges as well. Plus edges should be uncut edges. So let's define a new problem, max agreement with side constraints. So the input graph now contains labels for each edge, and the goal is to find a subset S that maximizes the agreement. And we still want the constraint of exactly bi nodes from each fi in the output S. So if we know how to solve max agreement with side constraint, we can solve fair max agreement constraint to 2 clusters as well, because we can define all the fi's to contain exactly the nodes of color I in the graph. Then we can create a series of instances to solve max agreement side constraints, and then we can choose the best solution which we've seen in this iteration. So let's say you have an instance with 2 colors and a uniform ratio between the colors. Then we'll start by assigning b1 equals b2 equals 1, solving the max agreement side constraint instance. And then we can assign b1 equals b2 equals 2 and solve this instance, and so on. And then we return the best solution which we've seen. So now we want to focus on how to solve max agreement sign constraint with a side constraint, because that will give us a solution to fair max agreement as well. The binary integer program for this problem is pretty straightforward. We have a variable xi for each node I, and if xy equals 1, it means that this node goes to S, and if xy equals 0, it means that this node goes to the complement of S. So let's see the SDP relaxation of this problem. It's a pretty straightforward sum of squares relaxation. Now we have a vector for each node. The constraints are coming from the sum of squares relaxation, are pretty straightforward. We're not going to go into details here. Just note that in the solution, we can get a marginal value for each node, which indicates the probability or how much this node is inclined to go to S. So now, when we have a solution to the SDP relaxation, let's see how to round it to an integral solution. To round the solution to the relaxation, we use Brownian motion. We call it a stochastic process. It's called a Brownian motion if it has independent increments. If the difference of the value of this process at different times is distributed normally with mean 0 and a variance, which is the difference between the times. And if this process B has continuous central path, it will be called the standard Brownian motion if the value at time 0 is also 0. We call that we can generalize it to an n-dimension process, and can add diffusion matrix sigma, and then the difference between the value of the process at different times is multivariate normally distributed with mean 0 and a covariance matrix which depends on this time difference and the diffusion matrix sigma. From the sum of squares relaxation, we get the marginal values and covariance matrix. To run this solution, we'll use the covariance matrix as a diffusion matrix for random process. So let's look at an example for two nodes. So we'll start an xy, which corresponds to the marginal values of this node. We'll perform a Brownian motion until we reach the boundary of the square. After that, we will continue with the one-dimensional Brownian motion until we reach the vertex of the square. So in this example, we reached 1 on 1. That means that these nodes go together to S. Let's now analyze the approximation ratio of the rounding process. To do that, let's look at two nodes, I and j. The starting point of these nodes is their marginal values, x and y. Now we want to ask ourselves, what is the probability that the plus edge between these nodes reaches 0, 0, or 1, 1? Or if they have a minus edge between them, then what is the probability that it reaches 0, 1, or 0, or 1, 0? And then these edges will be in agreement in the rounded solution. So let's denote this probability as U. So U depends on x, y, and the covariance matrix. We want to calculate this U for every x, y. If the x, y are on the boundary of the square, it's a pretty easy task, because then we have a Brownian motion on one dimension, and it's a martingale. So we can calculate, we can show a closed form for this probability, and we can do it for the whole boundary of the square. So that are the closed formulas which we get for minus edges and plus edges when x, y are on the boundary of the square. Now the next question is how to calculate this U if x, y are inside the square. So to do that, we can use a theorem which is taken from the book of stochastic differential equation. This theorem states that if we have a function on the boundary of the square and want to calculate the mean of this function on our stochastic process at the point where it hits the boundary of the square, then we can solve a matching Dirichlet problem. We can solve this Dirichlet problem numerically. Now we want to go through all configuration of marginal values and matching covariance matrix and find the minimum ratio between U, which is the probability, and the matching SDP value. This will give us the approximation ratio. By numerical calculation, we get an approximation factor of approximately 0.84. Note that the approximation factor for cut edges, that mean minus edges, was calculated in the previous work on max cut with side constraint. So if we stick this approximation factor to the formula which we saw previously of 2 times alpha divided by 2 plus alpha, we get an approximation factor of approximately 0.59 for the problem of fair correlation clustering with no restriction on the number of clusters. Let's conclude with open questions. The main question is, can we solve a constraint problem when it's constrained to more than 2 clusters and then achieve a better dependency between the constraint problem and the unconstrained problem? Now we have a bound of 2/3 for the unconstrained problem. Even if alpha equals 1 for the constraint problem to 2 clusters, we achieve only 2/3 for the unconstrained problem. So I think that's the main question. And thank you.